Welcome back to College Algebra, Math 1313. Today we're going to be looking at rates of change and behaviors of graphs. This will be section 3.3 in OpenStax. And just to remind you to make sure to be looking at that textbook and reading through the sections and trying some of the exercises before starting on the homeworks, and make yourself aware of the material before trying to start a homework and maybe get some wrong. So let's get started with the behaviors of graphs and the average rate of change. Today we are going to look at this thing that takes the shape of a lot of different forms throughout this course. You'll hear it called rate of change, in really specific cases the average rate of change. It's really closely related to slope, or you might hear it called change in y over change in x, or delta y over delta x, y2 minus y1, x2 minus x1. All of these things are different ways to look at this average rate of change, or when x is changing, y is also changing. So this will take the form of this formula as the most fundamental. This highlighted one is the most fundamental form of this formula. y2 minus y1, x2 minus x1. Another thing you might have heard at some point in your life is rise over run, where what changes vertically over what changes horizontally. That's kind of what we're going to be looking at today. So let's just start off real quick with a pretty simple slope calculation to get it rolling. So we've got some x values, some independent variable values, some inputs. I call them x1, x2. And then we got some y values, some dependent variables, some outputs. And then we're just going to plug those right into the formula that we've given up there above for the average rate of change, which is y2 minus y1 over x2 minus x1. And that's going to be 2.62 minus 2.31, all divided by 2006 minus 2005. And if you do your math well, 2 minus 1 is 1, 6 minus 3 is 3, 2 minus 2 is 0, over 1, because 6 minus 5 is 1, and I'm just going to leave it at 0.31. Well, there's your slope. There's your average rate of change in between 2005 and 2006. And if this is a linear function, which we have to check every instance to see if it is, then it should be a consistent rate of change no matter which numbers you pick. All right, so we're going to do the exact same thing, but we're going to take one step earlier. So for try it 2, we're going to take this one step earlier, and we're going to say, okay, they give us an interval. Really careful, it doesn't have parentheses, it's not a point. This is an x1 to x2 interval, and they didn't give us our y values. So it's going to be on us to find the y values and then on us to plug those in. And so our y1, or our f of x1, is going to be what happens if you just plug in that first x value. 1 minus 2 root 1, which is just going to be 1 minus 2, or negative 1. And our f of x2, be a little harder, but not too much. 9 minus 2 root 9, which is 9 minus 6, so that's just going to be 3. Or if you want to take it a step slower, 9 minus 2 times 3, 9 minus 6 is 3. So now I'm going to label those. It says f of x1, but if you really want to think about it in a different way, you could say that's y1 and y2. That's the output of the input of x1 and x2. And then we're going to take those four numbers and plug them all into this formula they gave us, this average rate of change formula, to come up with 3 minus negative 1. Careful with that negative sign. 9 minus 1, and we're going to end up with 4 over 8, also known as 1/2. So our average rate of change from 1 to 9 for that f of x is 1/2. That's pretty much how you solve average rate of change, and it's going to be how we solve slope when we're dealing with explicitly linear functions later on in this class. Quick note, just so you're like, well, why do we call them two different things? Because this average rate of change could apply to anything, any function ever. So let's say we have this crazy looking function that looks kind of like that, and I give you these 2 blue points, and I say find the average rate of change. Well, you could totally do it, and it would end up being the slope of that blue line. But that doesn't mean that the slope of the black line was the average rate of change. So that is the average rate of change represented by the blue line. And on a linear function, that will be the slope for the whole line. But that is the case where we would call it the slope. We would call it the slope if it was always exactly the same. We call it the average rate of change because it could be on a non-linear function, and we're still able to find it. All right, let's keep rolling. We're not going to do too many problems with this, but we're going to look at sections of a function, and we're going to say, okay, we can define the intervals where functions have specific characteristics. So for instance, right here where it's green, that function is from left to right going up. So we'll say that's increasing. And to define that interval, I don't know if it asks us to or not. It gives us the intervals. To define that interval of increasing, it's starting at negative infinity and it stops increasing right at -2. Then we've got, I'm going to draw it red, we've got a decreasing section. Looks like it's from -2 all the way to +2. And then it turns around and goes right back up from 2 to infinity. So it's just one characteristic of a graph. I don't have a practice problem for it, but you might see it in your homework and in the book, and you might be able to go find an exercise on it. But as you read from left to right, and if a function is increasing or decreasing, it's dependent on if it's going up or the y value is increasing, like in the two green sections, or decreasing, like the red section. Okay, last but not least is the two more features of a graph called minimum and maximums. So we really have four features that break out of minimums and maximums. We have local min and max, and we have absolute min and max. And we can just do example 10 to solidify what each of these is. And so a local min and max is when localized, so you zoom in. If you were to zoom in really big, and I can't zoom in that much, but if you were to zoom into that green square right there, if you found a point that could possibly be a maximum, no matter how far you zoomed in, then it's a local maximum. That means you were able to localize the function to make it a maximum. But for instance, no matter how far I zoom in here, that's never going to be the minimum because it doesn't turn around and go back up, right? So I don't know if it's going to keep going if that wasn't a dot. I don't know if it's going to turn around. I don't know if it's going to stop. I don't know if it's going to turn back around and not be a function because it's piecewise or some not function like a circle. And so when you zoom in far enough, you can tell what a local max is. So right there, we've got a local max and a local max, and we'll label those green things local maxes. And likewise, if we zoom in and we look at, find some interval, any interval on the left and the right where that becomes a minimum, we could zoom in right there and see, okay, that becomes a minimum on that interval. Then we have a local min. And then to find absolute maxes and absolute mins, we just look at the same intervals and we say, okay, but was there any spot, even if it wasn't local, that was lower? And for instance, right here, we would find ourselves having a absolute minimum. And is there anywhere in this function where it goes over the local maxes? It doesn't look like it, so we find ourselves at that top having an absolute max. And we will now look at how to write these things. So we'll start with what we started with, which was the local max. So local maximums are at x equals 2, y equals 16. And sometimes you'll see the word, actually, you'll see the local max is y equals 16, and it occurs at x equals 2. That's a pretty common way to see this, is they say, what is the local max and where is it? And it also is y equals 16 at x equals -2. All right, what about local mins? Well, there's only one on this one. The local min is y equals 0, and it occurs at x equals 0. And then we check for absolutes. This is a completely different calculation, but we're using those maxes and comparing them with the two endpoints, the farthest left endpoint and the farthest right endpoint, or perhaps an asymptote or some weird feature that might go over or under that local min or local max. And so we've got a absolute max. It's exactly the same. The absolute max is not going to be any different because there's no spot on the graph that goes above those two local maxes. And so we will just write the exact same thing for that. Copy that. That's not one to work with me, and that's okay. Is y equals 16 at x equals 2, and is y equals 16 at x equals -2, and our absolute minimum did change. Our absolute minimum changed because we had an endpoint that was lower than the local min. And so our absolute minimum is y equals, that looks like -10, at x equals 3. And there are some behaviors of graphs, some key features of graphs. If you wanted to go and hunt down the increasing and decreasing intervals on here, you totally could. Say there's an increasing interval there, and you could identify it using interval notation. Decreasing there, increasing there. That might be some good practice before you wrap up this video to see if you can remember how to write increasing and decreasing intervals. And then also, don't forget we talked about the average rate of change and that first introduction to slope and that first introduction to change in y over change in x. So, hope you have a good day. Thank you for paying attention for this long. I will see you tomorrow.